All right. There we go. All right. Let's so second lecture. Sorry I wasn't able to be here on Wednesday. I had a sick kid, so Tom's filled in for me. I heard you worked on units and conversions and uncertainty a little bit, sig figs maybe a little bit. We're gonna keep working on that stuff. I know it's not sig figs and measuring stuff doesn't seem that interesting unless you're a certain kind of person. Luckily for us, there is an entire government agency that's made up of that certain kind of person called National Institutes of Standards and Technology. If you are really into tracking down uncertainty and figuring out just how certain you can be about numbers, there's a whole career path for you if that's something that you're into. If you're not, then working on sig figs might feel a little bit frustrating because it does have certain very specific rules. And I'll just tell you this off the bat, that's the number one mistake that everybody in this room will make. It's the number one thing that I mark down every single class I teach is sig figs. So if we're going to do our best, and by the end of it, it's not going to make the difference between an A and a B in this class, whether or not you're good at sig figs. As long as you're okay at it, you can do it most of the time. Then you should still be able, it shouldn't be that much. Usually it's like, half a point on a 10-point question if you did everything right, but you got the sig figs wrong. So it's not that big of a deal, but we do need to be aware of it. And it actually does show up in everyday life. It doesn't seem like it, but your Apple Watch that tracks how far you're walking every day or when you're going for a run or things like that, that has actually uncertainty built into the programming. It doesn't show you 17 decimal places out on your distance because that would be overestimating or overrepresenting the certainty. So it actually is something, any digital number that you see, engineers and scientists that built that, actually, if they did their job properly, I don't want to assume that they did their job properly, but usually there's a lot of thought and effort that goes into just how many decimal places do we display, because your calculator answer is always going to give you a ton of them, right? So we'll keep working on that and talking about measurements and how to measure things. You talk about how to measure things like with a ruler a little bit. Okay, that'll be your lab next week. Your first actual hands-on lab will just be practice measuring stuff and writing down the right number of digits, which again, doesn't seem terribly interesting, but it is a good skill. And the more science classes you take, the more important that's going to be. And eventually it gets to the point where it's second nature and you don't have to think about it. But there's a lot of hard work between now and then. So first off, any questions anybody has? Just outstanding stuff. I think you worked on the conversions assignment yesterday. How did that go? Not well? Okay. Any specific questions you want to go over? I will put the key up this weekend, but go ahead. Just the word problems in general. So we're not going to work all the way through them right now because I do still want you to struggle with them a little bit. That sounds harsh, but you get a lot more out of it if you have to work through it yourself than you do if you're just following along with the key. Diego?
When was this assigned to?
It probably doesn't have a due date assigned to it on Canvas yet, but it'll be a week from yesterday. So next Thursday. So you still have some time. Yeah.
I was just wondering if you have like an uncertainty for sig figs, like plus or minus one decimal place or something. Sig fig on like tests. Because I know they did for physics last year.
Like a leeway. We're a little bit pickier in chemistry than physics is usually. But usually it's going to be like a quarter a point or a half point per decimal place that you added to you weren't supposed to. Does that make sense? Yeah. The other reason physics can get away with that is physics deals with a lot. I guess I can't say that because chemistry deals with those large numbers too. So I just won't say that. Yeah, go ahead.
What number or like above what number would you convert it with this
scientific notation or just leave it?
So you can put anything in scientific notation, like on the math review, I had you put it in scientific notation when it was just like what 2.15 or something like that was the answer. But the instructions very specifically said to put all your answers in scientific notation. What's this number in scientific notation? Times 10 to the 0. So you can do it anytime. Where you have to do it is anytime where if you didn't put it in scientific notation, you'd be left with an ambiguous number. An ambiguous number is a number where you're not sure how many sig figs it has. So if I write 5,120 meters, how many sig figs is that? Is it? Could be 4, could be 3. This is an ambiguous number. That's why we call it ambiguous, just means it's undefined. So it's an ambiguous number because it could be 3. We know it's at least 3 sig figs, but it might be 4 if I measured that last spot, right? So if we're not sure, this is when you actually want to make sure you put it in scientific notation, because if I write this in scientific notation, same number, but how many sig figs does it have? 3. Now we know for certain that it's 3 sig figs, right? So that's the only case where you must put it in scientific notation in order, or else it's going to be wrong. If you wrote this, I'm going to mark you down just like you rounded incorrectly. It'll be, and I'll just write AMB for ambiguous. Right, because I don't know if that's plus or minus 1 meter or plus or minus 10 meters. There's another way we can handle this as well. How else could we write this without using scientific notation that's not ambiguous? Good point. So if it happens to be plus or minus 1, we're going to deal with numbers that are a lot bigger and a lot smaller. So a lot of times we're not going to end at plus or minus 1 here. But it's not technically correct. It's sort of like shorthand. If you've seen this before, then you know that this is plus or minus 1. This is saying that the 0 counts as a sig fig, but it's not strictly speaking the most correct way to write it. That's not an officially correct way to show that that's a sig fig. Any other ways we could do it? What if we change the units? What if instead of 5,120 meters, what other unit could we use? Kilometers. What's the conversion for kilometers or for meters to kilometers?
1 kilometer, 1,000 meters.
1 kilometer is 1,000 meters. So if we did this, and a lot of times when I'm using these prefixes, I'll use just 10 to a power instead of writing out 1,000, but this means 1,000, right?
Yes.
Especially if we're doing something like 10 to the 6, I'm not going to write out 1,000,000, right? But if we write it like this, if we put it in kilometers, divide that by 1,000, that's not ambiguous anymore, right? So sometimes just switching the units is enough to make it so it's not ambiguous. Or if I specifically said your answer has to be in meters, then you would actually need to put it in scientific notation to avoid that. If I wrote like that, that would be 4 sig figs, right? That would be saying this is plus or minus 1. There's actually another reason why we use these prefixes. And it has to do with the limitations of the human brain. Basically, the human brain doesn't do well with numbers that are basically smaller than 1/3 or larger than 3. And actually, you can estimate in your head basically from about 1/10 to 10. But basically, if you have a number that's larger than that, than 10, What does 5,000 meters look like? What does 17 miles look like? If I asked you to just look at this classroom and say how many people are in it. Go ahead, look around. How many people are in this classroom? 20. That's probably pretty good. I'd say it's probably closer to 25, but basically our brains don't process numbers very well. In fact, if you actually need to count something that's more than 3 objects, what your brain instinctively does is it breaks it up into groups of 2 or 3 or 1. And then you do the addition to actually put those numbers together. And if you're paying attention, you can actually catch your brain doing this. Next time you have like, I don't know, like a handful of jelly beans and you want to just put them on the table and try and count them. Your brain will instinctively put it all into groups of 2 or 3 in order to count. So we don't do well with numbers that are bigger than 10 or smaller than a tenth, which is why these prefixes even exist in the first place. If I ask you how much 5 kilometers is, can anybody visualize 5 kilometers? Does anybody run a 5K? No? Yeah? Maybe? Even really big numbers, when you put them in the right units, all of a sudden start making more sense. What if I said 350 yards? Can you visualize that? What are you actually doing in your mind if you try to visualize it? You put it in football fields, right? Because 3.5 football fields makes more sense to visualize than 350 yards, even though they're the same number. And that's just because of the limits of the human brain. The human brain just doesn't do well with numbers outside that range of about 1/3 to 3. And that's just kind of a fun. The way that I describe it is we just lack the firmware. Our brain doesn't have the right programming to be able to actually process that. I've always thought that was really interesting, so I always make a point of talking about that. Any other questions about this? Any specific questions, not just the word problems in general? Does anybody try them, get hung up somewhere? All right. The clue that I'll give you for number 1. Did anybody solve number 1? How'd you do it? D equals MV, and that gets you what?
It's like the answer or like.
That'll get you the volume of the aluminum, right?
Yeah. Well, you solve for volumes because you're not given the length, so that's your X.
You're not given the length. What values are you given? Thickness, which is another way of saying height, right? Basically, treat the aluminum foil like it's a really, really short box. What's the equation for the formula, or the formula for the volume of the box? Length times width times height. Length is given, width is given. Instead of the word thickness, if you use height instead of thickness, that's given. And actually, we're trying to solve for length, right? So if we can figure out the volume from the density, then we're just solving for L. All right, and you can, if it's helpful, you can draw it out. Obviously, this isn't going to be the scale. But think of that sheet of aluminum foil as just a really, really squished box. You're solving for L. Here is your height, is your thickness, there's your width. And then, but we still need a volume to get there, right? So there's a couple ways that you can show your work to get the same answer for this. If you look at the equation for density, it's mass over volume. If you're given the density and you're given a mass, you can do some algebra to get to volume, right? I'm not always as big a fan of doing it this way. Because one, it means that you have to remember the equation for density, which is not, that's not a particularly tricky equation. It's going to be on your equation sheet that you're given at all times. But at the same time, anytime you've got what I call a combined unit, like grams per cubic centimeter, you could treat that as a density, you plug it in here and do algebra, but you can also just use grams per cubic centimeter as a conversion. If you say that I've got 1.10 kilograms, we can get from kilograms to grams, right? What's that conversion? It's 1,000 to 1, which direction? Is a gram bigger or smaller than a kilogram? Smaller, right? So 1 kilogram is 1,000 grams. And we'll get 1.10 times 10 to the 3 grams. Like I said, you can then take that and plug that in for mass and then solve for volume, or anytime you've got a combined unit like grams per cubic centimeter, that is a conversion. That is a conversion factor because it's saying for every 1 cubic centimeter, it's 2.70 grams. It's saying that those two things are equal. So we can say 2.70 grams equals 1 cubic centimeter. And the nice thing about this approach, instead of using the algebra, is that we're going to be dealing with a lot of combined units in this class. And so anytime you have a combined unit, this winds up being a really helpful way so that you don't have to memorize a whole bunch of equations or go look anything up. You just look at the units and you make the units work out. And this works for speed as well, right? Miles per hour, if you're trying to convert time into distance using speed of a car, for instance, this works the same way. If I gave you it as a mental arithmetic problem, if I said, you're driving 65 miles an hour, how far did you go in 2 hours? How do you do that? You're going to times 2. Well, why?
65 miles per hour.
2 hours is your amount of time, and for every 1 hour, it's 65 miles. So showing your work like this, and most people would have known how to do this. Oh, you take 2 times 65, right? Most of you would have known how to do this problem, answer this problem, without having to think about it too hard. But if you're not careful, you can really easily wind up dividing by 65 when you're supposed to multiply by 65. Showing your work and showing the units canceling out. And I think that you guys show your conversions as Tom's calling T-squares. Is that what I've heard? This is just the same thing. This is the way I've was always taught to write it. It's the same thing. This just is drawn out more like a multiplication problem. By doing the exact same thing. So if you set it up so that your units cancel out, you'll never go wrong this way. Make the units work, and then you're never going to divide when you're supposed to multiply. Right, and in this case, this is one that everybody knows how to do instinctively because this is an everyday sort of calculation, right? People think about this type of problem all the time. It's a little bit harder to see when it's something a little more abstract like a density, but it works the same way. Yeah.
Can you show us how you're dividing? Like, an equation when you're dividing instead of
Yeah, let's say we're taking our 65 miles per hour and we want to know how long it's going to take us to go 722 miles. We're trying to go 722 miles at 65 miles per hour. It's still 65 miles equals 1 hour, right? But we're just going to flip the top and bottom. We're allowed to do that because that's the top and bottom are still equal to each other, right? So if we're writing it like this, okay, well, we want to put miles on the bottom here. So we put 65 miles on bottom and 1 hour on top. So now miles cancels miles, will be left in hours. And the way you can plug this into your calculator, you can write 722 times and then put in parentheses 1 divided by 65, or you could just write it out as 722 divided by 65. Be the same thing mathematically, right? The way we do multiplication with fractions. So basically, when you're setting up these t-squares or any of these conversion problems, you're always just, if it's on the bottom half of your conversion factor, you're dividing by it. If it's on top, you're multiplying by it. Did that answer your question? All right, any other specific questions about these? Number 2 is just one long conversion problem. You can set them all up in a row, but basically you've got a bunch of combined units in that word problem there. Combined units like speed or like a density. For instance, 20 breaths per minute, that's a conversion. That means 1 minute equals 20 breaths. Now, breaths is a weird unit. We're not used to using that as a unit, but that still follows our same rules for these t-squares, right? So there's a whole bunch of weird units in here. And the final question is, how many milligrams of carbon monoxide does this person inhale in 8 hours? So if you've got a word problem like this and you're not sure where to start because you've got a whole bunch of numbers in there, if you think it's a conversion problem, if you can look at a bunch of these numbers that are given and say, oh, I can recognize those units, that's a conversion. Look for one of the numbers that's not a conversion. One of these numbers in here has units that are not a conversion factor. Anybody spot it? So is 15.0 ppm, is that a conversion? Parts per million. That means for every million pieces, you get 15 pieces of carbon monoxide. So that's a conversion. How about the 0.50 liters of air per breath? That's a conversion, right? Anytime you see the word per, that's a conversion. Because what does per mean? Divided by, it literally translates from Latin as for every. So 0.5 liters of air for every breath. That's a conversion, saying those two things are equal. 20 breaths per minute, that's a conversion. How many milligrams of carbon monoxide do you inhale in an 8-hour period? Is 8 hours a conversion? No. And then it gives you another one. It gives you a density in grams per liter of carbon monoxide, which is a conversion, right? So 8 hours is not a conversion. That's your clue that that's where you should start. Start with 8 hours and then just start trying to use these conversions that are given to you and to cancel stuff out until you're left in milligrams of CL. Right? And it can be helpful to write it out as what I call a roadmap. 8 hours. Hours is a time, right? Do any of these other conversions have time in them? Yeah. Breaths per minute, right? So if we went from 8 hours to minutes, and I'm not even going to worry about doing the math right now, but I know how you can do that conversion, right? So hours to minutes, and then if I can go from minutes to breaths. That's a weird unit, right? Which means it's not going to be on your conversion sheet. So where should you be looking? In the problem. The problem says 20 breaths per minute. And it also says 0.5 liters per breath. So once we get to breaths, we can get to liters. Once we get to liters, we could go to grams because we've got a density, right? And once you're in grams, milligrams. Right? So let the problem sort of lead you. If you can figure out where to start, then just start making units cancel out. Figure out how you have to, what conversions you have to do to use the pieces you're given. And that works as long as I don't do something really mean, like give you extra pieces of information. If I gave you an extra piece of information right there, I could really throw off that tactic, right? But for now, I'm not going to do that yet. I'm not gonna say I'm never gonna do that, but I'm not gonna do that yet. But the more practice you have with these sort of weird long conversions as word problems, the more you'll start to see patterns make sense and be able to start doing stuff like this in your head. The other approach you can do is you can actually start at the end and work backwards. If you know you need to get to milligrams of carbon monoxide, then you start looking for, well, what am I going to use to get to milligrams of carbon monoxide? Grams, right? You can use that same approach. And sometimes the way you get around having that extra information is if you start at the end and work backwards. Sometimes you're like, oh, I don't need that conversion. It's given to me, but I don't need it at all. It's easier to see sometimes when you start at the end and work backward. Three is going to take a lot of paper. So give yourself plenty of room, but it's basically just a little bit of it's some conversions mixed with a little bit of geometry. You just have to be able to look at convert radii into volumes of spheres. And it's safe to assume, it doesn't say it anywhere in here, but most planetary bodies or astronomical bodies are spherical. At least we can assume that they're close to spherical. So if you're given a radius and it asks you about things like volumes and densities and masses, you're going to use that radius to do what? Find the volume. Anybody know the equation for volume of a sphere? Pi r cubed. Right, so if you're given the radius, you can get the volume. This is also a good problem to be paying attention and get practice using what are called subscripts. Subscript is just a way to keep track of what volume you're talking about. This problem talks about volume of a black hole versus volume of the sun versus volume of the moon. Those are all spheres. They're all going to have similar equations, but different radii and different volumes. So the way you keep track of that is you say volume of the sun. You just write it as a subscript down below the rest of it. And that's a way that you can indicate, I'm talking about the volume of the sun, not the volume of the moon, not anything else. It's no math. It's just a way to keep track of this volume versus another volume. So we could say volume of the sun is 4/3 pi times the radius of the sun cubed. Right. Anytime you're doing algebra or math with the same variable but different values, that's a really useful tool, and we're going to use it a lot in this class. If you don't do that, it's just really easy to mix yourself up. Which volume was that I just calculated? It's, you can see why that'd be hard to keep track of, especially when you've got half a page of arithmetic and algebra sitting in front of you. All right. Any other specific questions about this assignment? Like I said, I'll put the key for this up. It'll probably go up on Sunday or Monday. But you'll have another chance after you see the key. You still will have a chance to ask me for more help with any of that before you have to turn it in. All right. Well, there was one other thing another really common error, and I'm going to remind you of this all the time, but it's just like sig figs. It's something that I see all the time. It's a really, really, I don't want to say it's a dumb mistake because it's really easy to do. And I've even made this mistake standing in front of the class before. With those metric prefixes, make sure that you write those conversions going the right way. Right? It's really easy if I say 512 grams and I want to convert that to kilograms. It's really easy to mix that up and say 1 gram is 10 to the 3 kilograms. Especially when you're going fast, right? Now, we can all look at that, and I think we all have enough experience with grams and kilograms to know that that's not true. There's not 1,000 kilograms in a gram. Right? 1,000 kilograms is a ton, literally. And a gram is tiny. It's a milliliter of water is a gram. So we all know that that's not true, but it's really easy to mix yourself up So anytime you're writing these conversions out, make sure you didn't do something silly like switch kilograms and grams, or switch the numbers that go with each one of them. The other one I see all the time, a little bit less obvious. What's the conversion for centimeters to inches? Anybody have that memorized yet? 2.54. Good. It's really easy to mix that up and say 1 centimeter is 2.54 inches. That would be really easy to do, right? Especially if you're not used to thinking in centimeters yet. But we all know that a centimeter is smaller than an inch. So we should be able to look at this and say, wait, I messed that up because I know that it's not 2.5 inches in 1 centimeter. Right? So just when you are writing out these problems, just take the time to give it a double check, what I call a reasonableness check. Did what I write actually make sense? And then the other thing I'll tell you is anytime you hit enter on a calculator, you should have a rough idea of what the answer should be before you hit enter. Because that's going to check you and keep you from making a really dumb calculator mistake. If you threw an extra 0 on something when you weren't supposed to, you'll catch that. If you have an idea, okay, I know that it's going to be, plus or minus 10%, I know it's going to be about 5 miles. And then if your calculator gives you 50 miles, that's a good reason to go double check to make sure you didn't mix up some numbers when you input them, right? Doesn't mean that you have to get it perfect every time, but it should at least give you a red flag, right? Every time you use a calculator, you want to have at least a general idea of what the number should be when it comes out, which is a habit that takes practice. So we'll continue to practice with that. When we do calculations up on the board, I'll stop and say, does that make sense? Is that about what it should be? I usually try to do it mentally, and I'll race you, see if I can get a decent answer on the board before you get it into your calculators. Just because that's a good way to practice having an idea of what it should be. All right. Then the last thing we didn't get to the other day. Let's talk about scientific method. Scientific method is something that you've heard it described before. And there's lots of different ways of diagramming it out to try and explain how it works. But basically, the scientific method is if you notice something is weird, try to figure out why it's weird. And basically, and this is something that we all do inherently. We all naturally try to have an idea of how things work or be able to predict things ahead of time. So with the science, you don't have to redraw this whole thing. The scientific method is basically just a way to formalize that idea. If you think that you understand how things work well enough to predict what's going to happen next, then there's one of two options. Either what happens next matches your prediction, or it doesn't. If the results are not consistent with your prediction, then you have to change your hypothesis. You have to change the way you're thinking about that system. Until when you do the experiment, you get what you're expecting to see. Right? So this bit right here is key. So we observe something, we're curious about it, we try to understand what's going on and make a prediction, and then we test it. If it doesn't work, then we have to change our hypothesis. So there's a couple key terms in here. What does a hypothesis mean? It's your prediction. It's sort of your understanding of what's going on. Hypothesis is, this is how I think things work. The hypothesis is what most people that aren't in the sciences, when they say it's just a theory, what they actually mean is that's my hypothesis. Because theory in science means something very different. That's one of the key points that I want to get across to everybody. When somebody says the theory of gravity, that doesn't mean that it hasn't been proven yet or it's not supported by evidence. Theory and law mean two different things in science compared to everyday life. And hypothesis is what most people mean when they say a theory. I've got a theory. What they really should say is I've got a hypothesis. All right, so there's a key distinction between the laws and theories. And I will tell you this right now, this will be on the final exam, probably on the midterm too. What's the difference between a scientific law and a scientific theory?
Theories can be disproved when they're down the water?
No, that's using that hypothesis can be disproved. And that's the one thing, that's the key point. I'm glad you said that because that's exactly the point. Theory versus law does not have anything to do with how well supported it is or whether it can be proven or disproven. Theory just explains why something happens, and a law just says that it will happen. In other words, a law predicts, theory explains. So we'll go back to gravity because I don't think that anybody is going to argue that gravity exists, right? But there is a law of gravitation, and then there's the theory of gravitation. The law of gravitation just says that two things that have mass are attracted to each other with this much force. The theory of gravitation explains why two things that have mass are attracted to each other. So it's not anything to do with how well supported it is. And it is entirely to do with, is it predicting or is it explaining? And the key that you want to make sure is can be proven false is your hypothesis. Right? So there's a really influential philosopher from the 20th century called Karl Popper. Karl Popper was one who actually he made the first major advance in the philosophy of science since about what 1200 AD. So the first time anybody put forth the scientific method and wrote it out. Does anybody want to guess where or when? I already gave you kind of a number for when. Anybody know the name of the person who discovered the scientific method? His name is Ibn al-Haytham. He was Persian. Everybody thinks that the Greeks invented scientific method. No, the Greeks they're really good at philosophy, which is basically just arguing. The Greeks were really good at arguing with each other. When we get into atomic theory, we'll talk about the history of it a little bit and Aristotle and what a jerk he was. But basically the Greeks, all they did was argue. They didn't actually do any science. They were really good at math, but not science. Ibn al-Haytham basically put forth the scientific method that basically said, if you have a hypothesis, you should test it. And if need be, you need to revise your hypothesis. What Karl Popper did, and then that lasted basically all the way through the Renaissance, through the Enlightenment, through the 1800s, the Industrial Revolution, all the way until the 20th century, where Karl Popper said, if you have a good hypothesis and a good theory, it should be able to be proven wrong. If you're saying your hypothesis correctly, you should be able to prove it wrong. If you can't test it and prove your hypothesis wrong, it's not science. Then it's something more like philosophy or religion. So that idea of falsifiability. We don't verify theories. We don't verify laws even. all we do is we get more evidence that our law or our theory is correct, but we don't prove it true. Scientific advances happen when you prove a hypothesis false. When it's false, that tells you that there's some improvement to be made. Something about the way that we're thinking about the world, or at least the system, isn't correct. And we need to change it. Karl Popper also, anybody taken philosophy? No philosophy here. Philosophy of science is a really specific niche of philosophy, but it has its own study. I believe, and it's been a long time since I took my philosophy, I think that's metaphysics. Anyway, I'll have to double check that. Anyway, what do you need to remember about this for this class? One, I just hope everybody comes out of this class with a little bit better understanding of what science is, even if it's not something I'm going to test you on. These three things, and the idea of a hypothesis is not the same as a theory, are the concepts I want you to take away from this slide. All right. Any questions on the scientific method? We've been talking about, let's talk a little bit more about uncertainty. We'll do the fun stuff first. All right. So what are we studying in chemistry? Yeah, go ahead. Kind of. You're always hoping your hypothesis is right. But if you're doing a good job as a scientist, you have to be able to test it in a way that it'll fall apart if it's not true. Kind of. I mean, I'm thinking of the best way to phrase this. Thank you. You're hoping it's right, but if you're doing your job, you'll let it be wrong if it needs to be wrong. You don't make the data fit your hypothesis. You let the data disprove your hypothesis if that's what happens. So that you know that you need to improve it.
Basically, the hypothesis is wrong, just saying that there's more to learn.
Exactly. But scientists are just people, right? And people are flawed. And people have a hypothesis that they think is right, and they will fight when they're presented with evidence that their hypothesis is wrong. Even the best scientists in history there's documented cases where they argue with the evidence because they don't like the implications. A good scientist shouldn't do that. Even Einstein famously did that when it came to quantum mechanics. Einstein hated quantum mechanics. And it was not because he thought it was wrong. Well, it was because he thought it was wrong, but it was because he didn't like the implication that the universe had randomness. And so instead of changing his hypothesis that, well, maybe the universe does have some randomness because all of this evidence shows that there's randomness, he just said, no, the universe can't be random. I don't believe it. That's not science anymore.
Quantum mechanics is like the whole Schrodinger's cat thing, right?
Yes, we'll get to that when we talk about electrons. We'll talk about how that behavior works, and we'll actually talk about Einstein and his debates with one of my favorite physicists is Niels Bohr. Boron's an element. Niels Bohr was the one who always had the quippy retort to Einstein. Einstein would say things like God does not play with dice because he didn't like the idea that quantum mechanics was random. Niels Bohr was the one who would chip back at him and say, well, Einstein, quit telling God what to do. So I like to use that as an example because Einstein gets held up as this paragon of like he's a really, really brilliant person, and he was, but he still wasn't perfect. He had his flaws. And that was a big one, is that he fought quantum mechanics, not because of the evidence, but because he didn't like it. Another example of a theory that's not falsifiable, so it's not really science. Who here has heard of multiverse theory? To some extent, right? The idea that there's an infinite number of universes out there. That's not really science because we can't test it. That might be true, but until we have a way of testing whether or not there are all these infinite universes, it's not science, it's more like philosophy and math. Leonora?
So can that not be qualified as a hypothesis until you have a sound way to test it?
It's not a good hypothesis. It's more like philosophy or religion at that point. And the math does bear it out to some extent, but it's contingent upon certain assumptions that you make. And you can if you start from different assumptions, you can get to a very different conclusion and still not make any logical, philosophical errors.
Hypothesis backed up by science, you have an experiment that you can use.
Yes. And sometimes you have to invent the experiment. If you're doing science, if you have a hypothesis, a big chunk of science is figuring out how do I test the hypothesis, not just what is the hypothesis. And a lot of that comes down to, well, if my hypothesis is true, this should happen. The other aspect of it is, if my hypothesis is false, it should fall apart when I do this. And then you do this to see if it falls apart. Going along with that whole idea that even scientists have their pet theories or pet hypotheses that they don't like to see disproven. It's been said that anytime there's a scientific revolution or new school of ideas, it's not, old scientists don't change their mind. They just die and get replaced by younger scientists that were taught the new school. So even scientists, especially as they get old, become set in their ways, and they kind of resist change and resist all new ideas because they've gone through 60 years of their life with a certain understanding of how things work. And when you're 75 and about to retire, the idea that you're going to have to upend everything that you've spent your life working on is not a very attractive idea. It's a reasonable human emotion, but it doesn't make it good science. All right, if we're going to study chemistry, this is just more prelude. So that since we spent some time talking about conversions and uncertainty already, if we're going to study chemistry, we should probably start with an idea of what chemistry is. And so this is just the Wikipedia definition of chemistry. Chemistry is the study of composition, structure, properties, and reactions of matter, which is kind of a broad definition, which is part of why I like chemistry. It's because it kind of means, well, everything. Anything that has mass and occupies space falls under the realm of chemistry. We get to study it all, which means those random chemistry questions that you're going to be asking every week when we do those quizzes can be about anything, really, anything that exists. The philosophical side of things, a little bit less so. I'll still usually try to answer those because those are usually interesting to me too. But basically, chemistry lets us study everything. And I always mention that depending on who you ask, what assumptions they make and what their background is, a lot of theoretical physicists will debate whether or not one means that two, or if they can be separate. Can you have something occupy volume without mass? Or can you have mass that doesn't occupy volume? But that's for the theoretical physicists to figure out. Basically, for us, under normal conditions, normal matter has both of these properties. If it has mass, it also takes up space. If it takes up space, it also has mass. Which means we get to study everything we can see, and a lot of things we can't. And one of the things that I like about chemistry is it's kind of in the middle of all other sciences. Because chemistry is the study of all matter, any science that has to do with matter is going to be involved in chemistry. And where these different fields overlap is a lot of times where the most interesting stuff is happening. Especially the newer the field, a lot of times seeing where a new field interacts with another field is going to really show you some really interesting things. So basically, modern medicine, you could describe it as basically where chemistry and biology overlap. If biology is just the study of living things and chemistry is the study of matter, modern medicine is basically how does matter affect life? And how do we promote that or control that or adjust that? All of those ideas are part of modern medicine and they all involve chemistry. And I always open it up. Can anybody think of a part of medicine that doesn't involve chemistry?
Like the placebo effect and something.
Oh, that's interesting because that's really psychology, but that does touch on medicine. So if we added another, if we made our Venn diagram even larger, if we put psychology right here, the placebo effect you could say is where biology and psychology overlap. Okay, that's a good one. We probably could explain it in terms of brain chemistry at some level, but that's pretty far removed. Neuroscience isn't there yet. Can anybody think anything else? It's really easy to find the obvious places where chemistry overlaps with biology, right? Like medications, pharmaceuticals, definitely. That's kind of like the definition of chemistry overlapping with biology is here's a new drug. What does it do in the human body? Does it fix anything? Say it again.
Stuff like stitches. I don't
Stitches?
really overlap.
That's getting around. Now we're getting into physics interacting with biology and bypassing chemistry. So you still have to sanitize it, right? That's chemistry. But yeah, you're right. That probably makes, and that's actually why one of my coworkers, and actually has anybody taken the dual physics here? With Dr. Orr? Okay, so two of our physicists at the college have degrees in molecular biophysics, which again kind of gets around chemistry. I would argue that it really is chemistry, but and definitely when you get into the realm of physical changes versus chemical changes. Okay, so there are two good ones. So there's one or two things out here on the side of biology that are still medicine. Is it modern medicine though? That's where I'll get you. It's not modern medicine because stitches have been around for thousands of years. I'm quibbling, but basically chemistry gets to touch all of these different fields. And if you're interested in going into a STEM field at any way, basically every STEM field has to take chemistry at some point. And if you really want to understand anything at a really high level, anything physical, there is some chemistry involved in it. So I just like this because this is kind of it shows how all these different fields are connected. And chemistry is connected to more of them than most of the others. Could be because I took this from a chemistry textbook, but let's not worry about that. But I know everybody in here probably hasn't decided what you're going to major in yet. Does anybody have any ideas in sciences? Anybody thinking? Bioengineering? That's actually, I was on the chemistry side of it, but my department in grad school was chemical and biological engineering. That's some really cool stuff that's happening there, but tissue engineering and things like that. And that's definitely getting into these three: chemical engineering, material science, and nanotechnology. Covers a lot of that stuff. Yeah, computer science is probably the furthest removed from chemistry. But if you really want to understand The other example I always use, anybody play guitar in here? Electric guitar? A little bit. Anybody like electric guitars or electric instruments in general? If you really dig into building guitars, then things like what types of magnets are used in the pickups makes a difference in the sound. And that's chemistry. Is it Alnico 5 or is it Alnico 1? All these different things are really, like the average person doesn't care, probably couldn't hear the difference. But if you really want to get into being an expert on any field that involves something physical, there's going to be chemistry at some point, which is kind of fun. All right. Let's talk about units. Look, I'm going to go fast through some of these. There's one more open-ended question. Can anybody think of a scientific field that you're interested in going into that's not on this? Yeah. Psychology it's up there past medicine and biology, right? But especially if you start looking at a lot of the current research in neuroscience, neurology, is a lot of that research is very heavily chemistry based. And if you're going to be a psychiatrist and prescribing medication too, then that's all chemistry more on the medicine side. But I would count. There's a good. There we go. There's a good web comic that's been around forever called XKCD. Sociologists. Sociology is just applied psychology. Psychology is just applied biology. Biology is just applied chemistry. And chemistry is just applied physics. It's nice to be on top, say the physicists. And then way over there, oh, hey, it's mathematicians. People argue about what are the hard sciences? The hard sciences, usually, sometimes people cut them off at chemistry is considered a hard science, and the rest of them are soft sciences. Sometimes the biologists like to draw that line right here, and the psychologists like to draw that line over here, and soft sciences, sociology and anthropology and things like that. Basically, you can argue about that sort of thing all the time, but it really is more of an interplay. It's not really all just one thing, and I'll be the first to admit that chemistry really is just applied physics. But I would just say math is just philosophy, though. So math isn't even its own field. It's just philosophy. It's really useful philosophy, but. All right. Let's talk about units some more. What is a unit? So just like before, I give you sorry, I'm trying to. There we go. The Wikipedia definition. A unit is a definite magnitude of a physical quality. In other words, all a unit is it tells us what a number means. A number without a unit is meaningless. It has no meaning. Again, philosophy, mathematics, mathematicians would argue with me on that one. But they'd be wrong. A unit gives a number meaning. Otherwise, if I said, oh, I'm this weekend I've got 5. Does that mean anything? No. You need more context. I've got 5 kids' basketball games I have to go to. Or I've got 5 movies I want to watch. Or I've got $5 in my bank account. Right? Those all give the number 5 different meanings. Those all could be considered units. Specifically, though, a unit is the whole piece of a definite magnitude. It doesn't just give a number. Doesn't just give a number meaning, it also gives it an objective amount of something. So mile is a length and so is a meter, right? but they're different magnitudes of the same physical quality. The physical quality is length. But 5 miles versus 5 meters, they're different in their definite magnitudes. Right? And then here's just some more examples. If you go to the gas station and you're paying in cash, you have to use a unit, or you have to rely on the person that you're talking to be able to infer a unit from context. If you go to buy gas with cash, you say, I'll have $50 of gas. Or if I went in and I said, I'll have 5 to the gas station attendant. That could mean dollars or gallons. They can't tell based on the context, right? The context matters, but if you want to avoid ambiguity, you have to be specific with your units. For the most part, this class, you're not going to have a number. Will not write a unitless number in this class. Sorry, I said that in a funky way. If you write a number on a piece of paper that you're turning in this class, it should have a unit or at least some context. There's a couple cases like ratios where you have to give your number context in another way. For instance, if I said 92%, that's percent seems like it should be a unit, but it's without more information. Sometimes our units are more like a description. So if I said 92% by mass or by volume, if I said that a particular beer was 8.2% ABV, all of that is one unit. The 8.2 doesn't mean anything without the percent. And ABV, what does ABV stand for? Is you're all under 21, so you shouldn't be drinking anyway. It's excusable to not know this. ABV means alcohol by volume. Basically, it's telling you what this percentage means. That is a unit, except it's not really a unit that you can convert. It's a unit that gives context by describing something. Right, another example, if you just said 400 milligrams of what? 400 milligrams of ibuprofen or 400 milligrams of acetaminophen? 400 milligrams of acetaminophen will probably kill you. 400 milligrams of ibuprofen is a pretty standard dose. That's 2 Advil pills. Right, so having context and having units is a big deal. And there's some really weird units out there too, because there's a lot of weird physical qualities that we try to measure. Anybody think of some other types of units? Got length on there. We've got dollars. What else? What other types of units are there? Luminescence, like lumens, is a really good example, because light is a really good example because there's actually about 4 different qualities of light that we actually measure. And they all have their own units. Frequency of light and wavelength of light and intensity of light, which is captured in lumens usually, are all different properties of light. And so they all need their own different units. Was there another hand over here? Calories. Calories is energy. Calories is also food, right? Calories is actually just the energy content of the food that you eat. Calories, anybody know what the definition of a calorie is? A calorie, you're right there. A calorie is the amount of energy it takes to raise 1 gram of water 1 degree Celsius. So it's actually a pretty, we already said 1 gram of water is like a milliliter. That's not very much, right? And 1 degree Celsius isn't very much. So that's actually not a very large amount of energy. The calories on your nutrition facts on your food is not actually that calorie. That's actually a kilocalorie. A kilocalorie is just 1,000 regular calories. However, because this is America and Americans are allergic to metric prefixes or something, they don't write kilocalorie. They just write calorie with a capital C. If you actually check your nutritional facts, if they did their job properly, it has to be written as a capital C calorie. That's actually means a kilocalorie or 1,000 regular calories. And if you get food from outside the US where they use the metric system, they usually will say kcals. Depending on where you get the bottle, a bottle of Coca-Cola from Mexico will say kcals on it instead of capital C calories, but it means the same thing. And energy actually has some really fun units. Barrels of oil equivalent is a energy unit. It's the amount of energy that you get if you burn an entire barrel of crude oil. Tons of TNT is an energy unit. What do we rank with tons of TNT? Explosions. Yeah, bombs basically. And it's literally TONNE of TNT is actually how you rank explosions or bombs during the war. The nuclear bombs that were dropped in Japan were, I think, 15 and 25 kilotons TNT. So 1,000 tons is 1 kiloton. So there were 15,000 tons of TNT was the equivalent of the bomb that was dropped on Hiroshima. That's still technically an energy unit. You can convert tons of TNT into calories or into barrels of oil equivalent. Those are all just energy units, which is kind of cool. There's a whole category. If you want to, it's Friday and we haven't done a whole lot in this class yet. You're not going to have too much in the way of homework. So we can spend if you want a good Wikipedia rabbit hole to go down this weekend. Wikipedia lists are some of my favorite things in the world. I love Wikipedia. Wikipedia really got started and became reliable when I was in college, and that corresponded to when I had internet for the first time in my life. We had dial-up when I was in high school, but we only had one phone line to my house, and so you were never allowed to be on the internet more than 10 minutes at a time because we didn't have call waiting or anything like that. So when I went to college and I had broadband internet for the first time, and Wikipedia was starting to get reliable, I used to spend hours just reading Wikipedia on everything from classic rock bands to science to to pop culture. And the lists that you find on Wikipedia are super fun and then there's also lists of lists. And then there's lists of lists of lists. So you can go down this rabbit hole where you say, okay, well, that's an interesting list of problems. And it's a list of problems. It's a list of lists of problems. So you can say, okay, well, how about philosophical problems? List of philosophical problems. And we have in the problem of criterion. You could just keep going and going and going. I highly recommend spending some time just playing around with the lists of lists. But the other one that I wanted to say is lists of units. There's lists of units that are regular units, and there's lists of strange units. Lists of unusual units of measurement. Horizontal pitch is a unit of length defined by Eurocard printed circuit board standard used to measure the horizontal width of rack-mounted electronic equipment. It's how wide a server is. That's a unit. So they actually define how big a server facility is based on how many of these horizontal pitch units you can fit. That's a unit of length. Rack units, light nanoseconds, metric foot. A horse length. Horse length has its own article. And then there's lists of humorous units. I like this one even more. A Sagan. Anybody know who Carl Sagan is? Anybody remember his most famous introduction to the original Cosmos series? He would say billions and billions of stars, to the point that he became known as it, and it wound up being assigned a quantity, billions and billions. What's the smallest amount that you can have that's billions and billions? It's 4 billion. So 4 billion of anything is a Sagan. A Beard second. Everybody knows what a light year is, right? Do you know what a Beard second is? A beard second is the length that the average male's beard grows in 1 second. There's barn. A barn is actually, there it is. A barn is a serious metric unit. You know that they're being serious because they tell you they're being serious. It's a serious metric unit that it's the cross section of a uranium nucleus. Because when they said it's the largest nucleus that they were practicing enriching with neutrons back during the Manhattan Project, and they said it was like hitting the broadside of a barn. So they said that area, the cross section of a uranium nucleus, is defined as a barn. One of my favorite ones, though, is, I don't know where it is on here, is Altuve's. Everybody know who Jose Altuve is? He's a very short, is he a shortstop or a second baseman for the Astros? He's 5'2", World Series champ. But in Houston, they used to report home runs and how many Altuve's is it. So just instead of reporting in how many feet, they said that was 102 Altuve's. Be a pretty big home run. But that's technically a unit. A unit is anything that we can use to give a number context. Donkey power, a third of a horsepower. A pirate ninja is defined as 1 kilowatt hour per Martian day. Some of the humorous ones, they're just making up stuff just because they can. The unusual ones, those are actually really units that get used in everyday life. These ones less so. A jiffy. It's between 1 and 10 milliseconds. A shake. A shake is 10 nanoseconds. Comes from the expression 2 shakes of a lamb's tail. Again, that's actually a real thing that gets used. They actually rank things in shakes in physics. Physicists are weird like that. All right. We're not getting anything more productive done today, so you can pack up. You can create whatever. When I was in high school, that was actually one of the units. We had to make our own unit system that we had to use for an entire week. And it was really obnoxious when you had to compare data with somebody else because they had their own unit system. He was really using that to make the point that we should need a standardized unit system, and that's why we use meters. No. So you're going to use this, and that was not on here, but basically I left off of that because we go. This would give you liters of air, right? But if you're in 15 parts per million by volume, that means for every million liters of air, that's 15 liters of carbon monoxide.